Subscribe and click the notification bell to stay updated with the latest videos from School of Technology, Management and Engineering and MIMS in.
I, Dhruv Jore, on behalf of NMIMS School of Technology, Management and Engineering family, welcome you all to AICTE Training and Learning Faculty Development Program on Internet of Things. Hope you all have enjoyed the previous session on data utilization with IoT. Before we start the session, I would like to inform you all that a feedback form would be floated in the chat box. So please fill the necessary details correctly, as attendance will be marked on the basis of the submission of the feedback forms only. The topic for today's session is data acquisition with IoT. So an IoT cloud is a massive network that supports IoT devices and applications. This includes underlying infrastructure, servers, and storage needed for real-time operations and processing. An IoT cloud also includes the services and standards necessary for connecting, managing, and securing different IoT devices and applications. Today, we have with us Dr. Gourinath Banda. He is currently an associate professor at IIT Indore, researching and teaching formal verification, cyber physical systems, IoT, and autonomous vehicles. He also has a great field experience as he worked as a chief engineer in Samsung. He completed his BTech in mechanical engineering. He completed his master's in mechatronics from Siddhant University and PhD in computer science from Rockfield University. We feel privileged to have you with us today, sir.
Am I audible, Dhruv?
Yes, sir.
Thanks. So we'll start the session for today. Actually, I'm on leave from IIT Indore. I'm in Denmark as of now, engaged as associate professor at Siddhant University. So I'll just share my screen. So all right, is my screen visible, Dhruv? Can you confirm?
Yes, sir. Yes, sir.
Right. So I'm on leave from IIT Indore. So currently I'm an associate professor in embedded technologies at Mads Classen Institute, University of Southern Denmark. So that is the reason we have got some glitches on the first day. Otherwise, I would have done this session on the first day, right? So we'll go through the journey of Internet of Things as it evolved. We'll take the track of embedded systems as our humble starting point. So as Dhruv already summarized, I don't want to spend much time. So these are my works related to embedded systems that you can see at the very bottom. We have developed a one IoT protocol version 1, 2, and 3, and also we are working currently on digital transformation using applied blockchain. And then we also have developed a real-time kernel that could be used for IoT deployments. Particularly, we have developed Harshark version 1 for single-core microcontroller boards, and Harshark version 2 for multi-core microcontrollers. Particularly, the single-core one was done for ST microelectronics board, STM. The dual-core version was developed for an NXB board. So in today's talk, I'll be taking you through an introduction on embedded systems perspective of IoT, because IoT existed far before the term Internet of Things has come up, partly because it has become popular because of the cost of internet service providers giving away IP addresses has gone down. So that made IoT paradigm a very affordable kind of architecture for many applications. So particularly embedded systems were there, and then came the era of cyber physical systems, and then a category of cyber physical systems could be called as Internet of Things. Then we have another category where Internet protocol is not available at the end device. Then we qualify them as wireless sensor networks, right, or WSN nodes. Then I'll go through one of the earlier work that we did in IoT, where we developed the one IoT protocol. I'll just go through that in detail. Then I'll conclude the session by introducing you a real-time kernel that is developed in our group, right, during my days at Denmark as well as at IIT Indore. Right. So embedded systems are not new, right? Because most of us in India or across the globe, we have been using, like for instance, microwave oven. Might not be aware that it is an embedded system example. The simplest embedded system which everyone in India might have seen, at least those visiting a city, are the ones deployed in traffic signaling system. Little bit advanced societies might have seen in India washing machines and dryers, which do have. And the earliest example for an embedded system is a simple digital clock, right? Of course, there is no much continuous interaction other than setting the time, date, and all that. But the only output such a humble embedded system had to give in the initial days was just displaying the time, as well as reading out the time or ringing when an alarm set has matched with the current time, right? So these are examples for embedded systems deployed in household. For instance, when you bring such embedded systems online by allocating them an IP address and giving them modality to be controlled from a different device that is also connected via IP protocol, we qualify such systems as Internet of Things compliant embedded systems. Like for instance, I don't want to use the term IoT because IoT is a very restricted version of embedded systems. But anyway, this session is on IoT systems, so we'll be taking that perspective of embedded systems on this IoT paradigm. Like for instance, most of the advanced systems in the civilization, for instance, space systems as well as aviation systems, they do make use of embedded systems as well as IoT, right? So wherever we see automation, there we have an embedded system present always, right? That is a message you should take. For instance, military system applications, not necessarily military, Navy as well as Air Force, they do have advanced systems which are realized through an embedded system. Maybe that takes the form of an Internet of Things or a cyber physical system or WSN. So essentially, from a computer systems or computer science and engineering perspective, we need to understand first what is at the core of an IoT, which is an embedded system, and we need to understand what is its essential behavior, right, from a systems perspective, like what is its input, what it does after receiving input, and how it gives out output, right? So for instance, if you take a simple washing machine, right, washing machine, as in these days we have got top load, front load, and all those kind of versions, but irrespective of whatever be the direction of loading, most of them, or if not all of them, have got an embedded system inside it. So if you see in this washing machine, you have got a knob to select the washing program, which is connected to a microcontroller's
Excuse me, sir.
pins. Hello.
Sir, actually, I think the screen is not changing. Only the initial slide is on the display.
Oh.
Yes, sir.
Okay, so what should I do now? Okay, let me do.
So you have to screen share the whole screen, I guess.
Okay, fine. So yeah, thanks for that. Then I'll do the whole screen share. Okay, let's go. Is it coming up now properly, Dhruv?
Yes, sir. The fifth. Are you on fifth slide? The fifth slide is visible.
Can you read the title of the slide and this?
Embedded systems, IoT, CPS, WSN.
Okay.
aerospace, civilian applications.
Yes, yes, yeah, thanks. So we do have various incarnations in military domain or navy domain or aviation domain. But let's understand what makes first the essential component of an IoT, which is an embedded system in the first place. Let's take a simple example of a washing machine, right? You might have seen a washing machine has got various offerings, top load or vertical load. Whatever be the loading direction, it is usually having a knob that lets you to do a power on or off, and a program selection together with some buttons to choose some advanced features. And there is a small display panel that shows what is the mode of operation of the washing machine. So this is a bigger system, and the system which is embedded inside it, that is automating the ultimate functionality being delivered by the system, is called as an embedded system. So as the name says, the system that is embedded inside a bigger system is called an embedded system, right? So usually it has got an input interface. For instance, in this case, all these four are input interfaces. Maybe these are all push button kind of buttons, and this could be a kind of multi-step button, which is a kind of rotary type of button. So once an embedded system receives its input, the system is configured to deliver a functionality, and on turning on the play button on the washing machine, what it does is these inputs are read by the control unit. A control unit consists of a processor, including with an inbuilt RAM, inbuilt ROM, and with some software that is running inside the processor. Once these inputs are received, depending on the program selected, the processors or microcontrollers output pins are connected to appropriate display or appropriate output drivers. For instance, if it is a kind of motor that is rotating the drum in here, then the pins for the motion control are connected to the driver of this motor. And for instance, if it needs to give out some critical information to the user, for instance, it could be the how much time is remaining, or what is the current RPM, or the modes of operation of the machine is in currently, then we can be using a simple driver connected to its display, right? This is a simple embedded system, which these days in India we have got various solutions from LG, Samsung, of course these days V-Guard and all these guys. They are making it possible to control your washing machine through an app on your mobile phone. So qualifying such a simple embedded system inside a washing machine to be qualified as an Internet of Things compliant system, right? That is how we have. So basically, an IoT is basically an embedded system which is enabling the functionality of a very bigger system, but it is connected to Internet protocol through a unique IP address that is allocated to this embedded system, right? So that is how we need to understand what is an IoT node and what qualifies, or when an embedded system becomes to be qualified to be called as an IoT node. So embedded systems can be looked from a typical computer or PC block diagram like this. You have got a microcontroller, which is the core of the embedded system, that is reading the inputs from the input pins of the main system, and it might be having access to an additional memory, right? In addition to what is inbuilt in the system code. Together, there could be interfaces with other devices. Right? For instance, if this embedded system is an IoT device, then the system core might be talking to a communication controller, which is connected to an Ethernet controller, which itself is connected to an IP gateway, right? Or it could be a Wi-Fi module, which handshakes with the modem's Wi-Fi, right? So on the other hand, this system core will be driving its outputs through appropriate drivers through its output ports, and it can control the output devices. So for instance, if you take a look on microwave oven controller, like for instance, simple on-off kind of embedded system. So let's see what are its input panel consisting of, right? So it could be having a front panel that is having various buttons to select the kind of operation. It should be at level 1, level 2, or level 3 kind of thing. Or you can also key in how much time the machine should be on, or after how long the machine should be turned on, like that. Then you will be having a kind of door, which might be having a kind of infrared obstacle point, which when closed means that when the absence of infrared inclining on certain point, it means that the door is closed. Then you will be having a kind of beeper, which is a kind of output. You should remember the direction of the arrow lets you to understand whether it is an output device or input component. Right? For instance, in the microwave oven, there's a microwave tube which generates a microwave that when incidences on the food, if it contains some kind of liquid component, then the liquid gets heated and eventually the food gets heated. Right? This is an important actuator of a microwave oven. Accordingly, sometimes, when you take a microwave oven to maintenance department of a seller, then there is some port which could be connected to the diagnostics computer, and they can check what is the status of the device as of now. Alternatively, you might be having, as we have seen, there's a small display panel, which would be, of course, these days some of the microwaves do have some speaker system that translates text to speak or text to sound, right? And of course, there is a kind of light inside the microwave oven. Depending on the mode of operation, the light could be turned off when the door is closed, or it could be turned on when the door is closed, or the otherwise, right? So basically, and there is a plate at the bottom of the microwave oven, right? Usually what it does is when the oven is turned on, in order to make a homogeneous exposure of the food with respect to the microwaves generated by the tube, the plate would be rotated. Right? These are simple things, but that should let you understand a microwave oven has got an embedded system which consists of a microcontroller that has got a couple of inputs, as you see the arrows that are inbound, and there are a couple of outputs as the arrows that are outbound. Right? Another version of embedded systems or even IoT systems that are being used very much in the industry are the data acquisition systems, right? Basically, in data acquisition systems, what we have is there is some sensor which collects some kind of signal from the plant or the phenomena that is being observed. And then there is a kind of, the sensor translates that physical signal into a signal, which is then conditioned, like, linearization, filtering, and all that stuff. Then we do a kind of translation of analog to digital conversion, which is then fed into the input port of the microcontroller. Right? This is how the input looks like. So this is a kind of binary, this is a physical signal, which is translated into a binary signal, and even then it is being read by the computer. Then we have got another version of embedded systems that are being used as monitoring and control systems, which will be spending some time to understand what they comprise of. So this is a typical reconfigurable input output system. As you can see, it's very much heavy. What should you understand from this is that it is a very generic input output system that lets you to collect signals from various traditional or legacy ports, right? Because there could be various sensors or interfaces on the devices that will be generating some signals. For instance, in this National Instruments Compact Rio, what we are having is we are having an integrated processor IO, right? So basically, it is accepting gigabit Ethernet, USB, serial SD, mini display ports as its inputs, and then there is a kind of processor interface which could be connected to the processor board. Then it has got FPGA boards as well, right? Xilinx board, which is specifically on Zinc 7000. Then it is also having some kind of modular IO corresponding to various traditional or legacy signals that could be processed by this Rio. Another interesting incarnation of an IoT or embedded system is a patient monitoring system, right? Basically, a patient monitoring system should have some interface to read vital statistics of the patient to which that system is attached. For instance, there could be a sensor attached to the wrist of the patient or to the back of the patient that is responsible to report what is the XYZ coordinates and what is the UV y coordinates or velocities, right? So that is being translated into A to D, and then it is being read by the microcontroller on the board. Or it could be, blood pressure or atmospheric pressure, temperature sensor, humidity sensor, what is the saturation point of oxygen, what is the ECG signal of the heart through the pulse on the wrist, or it could be directly from the pulse or some kind of observed phenomena on the blood in a finger. Like, these days during COVID, you might have seen there is this, pulse oximeter. That is a simple example of a patient monitoring system, but of course it is a standalone. But there are patient monitoring systems or pulse oximeters that are connected to your mobile phone, or you can connect the pulse oximeter to a internet through Wi-Fi, and then you can connect your mobile phone also to the same Wi-Fi and get access to the pulse oximeters readings. And likewise, you might be having, toxic gas sensor, so that, for instance, if there is some leakage in the environment where the patient is, then the corresponding rescue teams would be alarmed. Air quality sensor, for instance, some of the patients who are in coma might be requiring some amount of oxygen at certain levels of delivery, right? If that quality falls, then there is a need to it to be reported to the corresponding technician or caretaker. On the right hand, you are seeing that there are some outputs that are coming out of the microcontroller. For instance, it is an output going to the LCD display that shows what is the current state of vital statistics of the patient. Then there could be, GPS system, right? So basically it locates where the patient is moving about. Then there is kind of, alarm that would be rang either to report the patient or the caretaker, right? And you have got the GSM GPRS module that lets to connect the patient monitoring system online, right? Basically, GPRS or GSM is the starting point of a radio devices to get an IP address, right? So basically, this GSM GPRS module is the one that is taking care of reporting the situation of the patient, either if by configuration to a certain SMS, so into a specific mobile number, or it could be connected to a Wi-Fi by means of data connected to a cloud server, which reports various monitoring data on a unique web interface. Right. So there are various kinds of embedded systems or IoT depending on what are the characteristics of the parameters that are being read by it. Right. For instance, these are the things these are the informations about various continuous and discrete systems that is provided by Professor Do Sullivan on his notes. So you can see that product output measures, for instance, if it is a weights, liquid volume, solid volume, that could be continuous control. But on the other hand, let's say you are using some system to count number of people coming into a university, right? That's an example for a discrete signal, right? And then it could be a kind of quality measures, like for instance, if it is consistency, concentration, contaminants concentration, conformance, these are all continuous values. On the other hand, discrete dimensions could be, absence of defect. It's a yes or no kind of answer. Product reliability, yes or no kind of answer. And then when we come to variables and parameters, they also fall under two categories. Some variables need to be in the continuous domain, that is real domain. For instance, temperature, volume flow, pressure, etc. are on the real. But however, discrete control, of course, in this case, it is just given like that. But there are controls where velocity is also in the continuous domain. That apart, let's say, for instance, if we are talking about some sensors that are reading flow, they are continuous sensors, or the ones that are reading temperature, for instance, thermocouples, they are also under continuous control. Pressure sensors also form. However, photoelectric sensors, or like, let's say, infrared sensors, strain gauges, piezoelectric sensors, they are discrete control elements. When it comes to actuators, we have got valves, pumps, heaters that are also under the category of continuous. On the other hand, when we have switches and discrete digital motors, these things are discrete actuators. like process time constraints, right? So you have got various possibilities. So again, I'm using the word embedded systems again and again because at core, the final component in an IoT is an embedded system, right? And that component might be required to have a hard real-time behavior or a soft real-time behavior. For instance, you can see in here, this slide summarizes the embedded systems that are deployed in an aeroplane system or in an autonomous car or a simple car or a kind of remote mission running on top of Mars planet, or you are having some embedded system being used on all-terrain vehicles by military people, and you also have some kind of advanced systems that are deployed in space applications, right? These are all the examples of embedded systems or IoT systems deployed in hard real-time applications versus soft real-time applications, right? For instance, if you see in here, there are real-time systems that are deployed in level 0 autonomy, level 1, level 2. For instance, there are autonomous vehicles. As of now in India, we only have cruise control, so it is only up to level 2, right? So on the other hand, when we talk of realizing IoT systems that need to have a real-time behavior or hard real-time behavior, then it is recommended that such an IoT system should be implemented on top of a real-time operating system or a real-time kernel, because the application developers or IoT application developers need to focus on their end application rather than certain deadlines or temporality related functionality to be realized in the software. We'll see that at the end, to more very much detail into a real-time kernel that we have developed at IIT. So let's understand first, because again and again I am using the word embedded system. Maybe you know it, but it is always better to have a kind of hands-on knowledge when you go for the clarity on IoT architecture, right? For instance, let's take a simple, this is a sensor system used in a gas bottling plant. For instance, if you go to an Indian gas station where they are refilling the tanks or cylinders, then usually it is mandatory that we need to keep track of there is no leakage of LPG in the shop floor, otherwise it would cause an explosion. So we use a network of sensors spread across the entire floor area that always keep track of how much amount of LPG has been leaked into the air, so that if it is beyond certain threshold, the control program in the controller triggers an alarm. So whenever certain volume of LPG gas is identified beyond certain threshold, then the alarm starts ringing, right? So this is an example for a simple embedded system. But when such embedded systems, if we add another board of communication controller which brings the behavior of this entire alarm system online, then that becomes a kind of IoT compliant embedded system, right? For instance, if you take a look what exactly this software in the embedded system does, is something like this. So this is your microcontroller board, right, which has got an input interface, which has got an output interface. So basically, this arrow that is going in here, I mean, we are zooming into that. Whatever is the box in here, that is, we are zooming into that, and accordingly we are seeing it. So basically, that input from the sensor is going to a kind of analog to digital converter. Then it gets read by the program being executed by the microcontroller, and then we also have an output interface. After this program has processed the inputs, it computes the outputs which are driven onto the actuators, right? This corresponds to this output corresponds to this point in here, right? Then, as I told, embedded systems or even IoT systems could be qualified based on functional requirements and hardware capabilities. So let's take a look on most of the IoT systems are either on-off control systems or some kind of sophisticated control systems or data acquisition systems or data report systems, right? So for instance, in this case, we are showing, when a system is some embodiment that accepts certain inputs and generates some outputs, right? That is the thing. For instance, in the case of an accelerator of a car, what we have is that we have a throttle system that accepts the pedal angle as its input, and accordingly the throttle valve is controlled, and then it appears the theta is directly influencing the velocity of the vehicle, right? That is how a simple control system could be envisaged, right? For instance, in the case of a automated driving system, what you have in here is, okay, I don't know why this is gone here. Am I audible, Dhruv? Hello?
Yes, sir.
Okay, fine. So this is a simple autonomous system having a kind of cruise control. What is happening in here is, there are some sensors that are sensing the current actual velocity of the car, and then there is a desired set point, which both are being read by the cruise control system, and the output is generated, or throttle is pressed such a way, or the angle of throttle is done such a way that the difference between the desired velocity and the current velocity is minimized or at least zero. Right, that is what is happening. For instance, if it is a kind of temperature control system, so let's see a simple system in here where we have a tank which is having a water inflow, and then what is happening in here is there's a hot steam that is coming in, which gets cooled after exchanging heat with the liquid in here, and it goes out. Basically, the rate at which the steam is coming in is controlled by this valve, and accordingly the rate at which this liquid could be heated depends on two parameters. One is the rate of inflow as well as the rate at which the steam is being circulated, right? So these are controlled for optimal controlling of set point of this fluid's temperature. Let's not spend time. Another example for a IoT enabled embedded system these days, for instance, Kuna and Johnson, Otis, these people are having IoT compliant lift controllers, right? They use PLCs with a means to interface with that. However, they cannot control the lift from the IoT, but they can report diagnostics. Since each of their PLC system used in the lift control system is having an IoT or IP address, then that qualifies their lift controllers as IoT nodes. This is a kind of lift controller or lift deployment in certain part of Germany. So if you look into a lift system, what is it having? If you see in here, you can see that a lift system is nothing but an embedded system, because there is a panel in here and also LED showing what floor we are in, and there is a motor in here which, when controlled, slides this vessel up and down, and then there is an actuator on the doors which, when the lift is in transit, is locked or it's open when the lift comes to a stationary point, and those doors could be either motorized or manually driven. So there is a kind of block diagram of this lift system. For instance, take a look on how these things are working. So basically there is an elevator car, right? So elevator car is always connected to a sensor that reads at which floor the lift car is now. Then it is also having a kind of floor indicator, right? So inside the lift you might be having a floor button, floor lamp, direction lamp, and all that stuff. So Dhruv, like how we take the sessions, like every half an hour, couple of minutes break, or every 1 hour break, or no break? Hello.
Yes, sir.
Like, is there a need for giving a break after every half an hour? I mean, otherwise people will become.
No, sir. No, sir. A session continues till it ends.
Okay, fine. Yeah, I mean, that's okay. That's the organizer's perspective. But if any of the participants wants to take a break, let me know. We can have 1 or 2 minutes break and then we can pull up. Can some of the participants speak out? Because I usually like to interact with the participants rather than with the organizers.
Sir, actually, they can interact with the chat.
Okay, so they cannot speak here?
Yes, sir. Yes, sir. They cannot.
Oh, so I'm not seeing. Okay, one second. So where is the chat window? Okay, I'm not able to see the chat window. So is there any specific chat window?
No, sir, not as such. This is only the chat window, but if anyone would have any doubt, he could ask.
Okay.
Yes,
Great.
sir.
Right. So let me continue then. So let's understand now a little bit of internal details of what comprises. Okay, it's here. So for instance, typically, let's take an example of an IoT enabled incubator system. Right? Incubator is the one that is used to maintain the temperature. For instance, if it is a kind of baby incubator, then the idea is it has got critical life support systems inside a small confinement, and the temperature inside that control volume is kept at 38.6 degrees centigrade. Right? That is how the temperature is maintained. Then you have got this various sensors in the incubator system. For instance, there is an electronic thermometer, then there's an electronic hygrometer. Hygrometer is the one that senses what is the humidity inside the control volume of the incubator. And then there's a e-gas sensor that records what is the level of carbon dioxide that is getting released by the baby. Or you will be having electronic gas sensor that identifies how much oxygen is being pumped by the oxygen supply pipe into the incubator, right? Because the baby needs good amount of oxygen on a second by second basis. Then the incubator system would be having actuators, which are like air conditioning elements. In the air conditioning element, usually it has got a kind of controlling of a heat as well as water vapor in the air. Then you have got oxygen valve to regulate oxygen contents in the incubation chamber. Typically, the software implements a simple while true routine, like it reads the temperature, humidity level, and oxygen level, and pre-processes this value and identifies if those values are less than the required things, and accordingly turns on the heater. If the temperature is okay, then it turns off the air conditioning element. Else, if the temperature is greater than C, then what it does is it kind of, if the heater is turned off, you need to turn off the heater, then you turn off the air conditioning element. If the humidity is less than 30 degrees, then you need to turn on the vapor conditioner. Vapor conditioner is nothing but there would be a kind of water along with a heating element. If the humidity goes down, the heater is turned on, and when the water reaches boiling point, the air gets diffused with humidified air. If the oxygen level is below 89, then we'll be turning on the oxygen valve inside the incubator. If the chamber is open, then we need to have a constant input of heat. Otherwise, it all depends on in which kind of an environment the incubator. If the environment is in the hot condition, then air conditioning element should be turned on. If the incubator is in the cold condition, then heater element should be turned on when the doors are open. And accordingly, once this is done, recall that such a system has got how many? 3 actuators. One is air conditioning element, oxygen valve control, and heating element. All those are controlled according to what is the calculation of the control that is happening in the then statement. So generally, the program inside an embedded system looks like, there are usually 4 steps. First is reading the inputs from the sensors. Then in step 2, we do a kind of pre-processing, and in step 3, we do a kind of control calculation, and in step 4, we do. So Dhruv, there is one guy who is in the waiting room, so please take him in. Right, and in step 4, we drive the outputs corresponding to the various output drivers. Let's take a look on how a control system essentially looks, or IoT system essentially looks. Generally, an IoT system can be looked up as a controller, and its surroundings could be considered as a plant. And this IoT system would be giving out from time to time certain outputs to the plant. These are the outputs U1, U2, UN. That means there are n outputs. And from the plant, it is taking in certain inputs, Y1, Y2, yn. There is an equivalence of n is equal to n here, but it may not be the case. Right?
I think that sir has disconnected. We'll wait for a few minutes for him to rejoin. Sir?
Okay, yeah. So I lost the connection in between.
Yes, sir. No
So
problem.
yeah, so I could, okay, fine. Yeah, I'll continue. So I'll share the screen again.
Yes, sir.
Right. So basically, if you take a simple look on how the control system looks like for that simple control system, what you can see is this is how the things are like. You will be having a microcontroller that keeps track of what is the required temperature, and from time to time it drives some signal into the tank, and from tank through its thermometer it will taking the um, input, right? So that is how it is working, right? So I don't know why it's this is coming in picture. Yeah, right. So we need to understand that in an IoT we have got this controller that is uniquely identified by an IP address, and once that happens, it qualifies to be called as an IoT enabled system. So you have got this we can refine that block diagram further, because you will be having your control computer which is connected to the internet. Then what it does is it has got some set of sensors S1, S2, S3, Sn. Then it has got actuators A1 to AM. So plant is being monitored by the control computer by reading the parameters of the plant through these sensors. and the output is being input on the plant through this actuators A1 to AN. Right, that is how the things are. So let me move this around. So to understand, in essence, an IoT is such an embedded system, right? On this right-hand side, you'll be having your hardware part of the IoT, which is in this digital controller. There might be a module that directly connects it to the internet, as we'll be seeing in the third part of this today's presentation. What qualifies a embedded system to be called as an IoT enabled device? So plant is being read through sensors, and computation is being carried out by the digital controller. Based on the situation analysis, it computes what actuators needs to be turned on and at what level. That is being delivered through the actuators, and this actuators interact with the plant. So let's see. There is during the initial set of slides, we have seen that these are embedded systems that are standalone embedded systems, right? But for instance, some interesting and grandeur behavior is possible if we can connect these embedded systems through a networking concept, right? We'll be seeing what is a CPS, but just to understand that there's a network of embedded systems, and each of this dot in here that you are seeing, each dot in itself might be having sensors and actuators together with a microcontroller, and also a communication controller through which it is able to network with the other embedded systems that are either located in the same location or geographically separated, right? So this is a kind of network of embedded systems. But one more thing, you should understand that even a standalone or single processor embedded system could be distributed on its own. Like for instance, as you are seeing in here, this plant could be monitored or read by this sensor, but the connection from the sensor to the digital controller need not be through a physical wire. That itself could be IP enabled, or that itself could be some kind of proprietary protocol enabled Wi-Fi connectivity. Right? In that case, what we are having, it is still a single processor embedded system, but it is a distributed embedded system. You should understand that we could have multi-processor distributed applications, like in the case of an IoT, or it could be a kind of single controller, but yet distributed embedded system, where in such case, what happens is the sensor actuator might be connected to the controller through a proprietary network protocol. So basically, remember that when you have such a network of embedded systems, some additional synergetic functionality is possible. So as I told, each of this node inside this network embedded systems itself would be having all these things. Of course, the plant itself might be a local plant, or it could be a kind of, the plant might be distributed on itself. So remember that this lines in here, that is transmission and reception, or transceiving that we call, might be through typical IP protocol, in which case each of these node is having its own IP allocation scheme, or it is natively IP enabled, right? On the other hand, if there is no such IP enabling at the node, but still there could be a kind of proprietary Wi-Fi connectivity. It could be Bluetooth, it could be some kind of IEEE low PAN connectivity and all that stuff, in which case this network qualifies to be called as a wireless sensor network, and each node is called as a WSN node, or wireless sensor network node. Now let's understand, these days people are a little bit confused, saying that there are IoT systems which are also qualified to be called a cyber physical system. The answer is no. Not every IoT system could be called as a cyber physical system, and not every cyber physical should be or is qualified to be called as an IoT. That's the reason is simple. You can see in here, there are embedded systems that are network embedded systems, but need not be internet enabled, right? In which case they do not qualify to be called as an Internet of Things, right? So that is the reason. So let's understand first, what is the subtle difference between a typical embedded system and a cyber physical system, right? If you see in here, it's an overlay diagram. At the bottom, you are having plant. You on the right hand side, this is your digital controller. And this digital controller would be connected through sensor to sensors via an analog to digital, right? So basically, this sensor, actuator, and digital part comprise the cyber part of the system, whereas the plant sensor and actuators could be called as physical part. That is the reason it is called as a cyber physical system. But it is not the case that every embedded system could be called as a cyber physical system as well, because not every embedded system have all these characteristics. What makes a cyber physical system is that these are the systems involving tight integration between physical plants, cyber processes of digital controllers, and communication processes, right? So basically, cyber physical systems are systems where there's a tight integration between cyber processes and the physical process or continuous physical processes. Dhruv, you are seeing that there are two people who are trying to enter into the room. Can you please take them in? Dhruv, am I audible?
Yes, sir. I have done that.
Okay. So again, some guy is still waiting. So please look in that because it is coming on top of the display.
Yes, sir. I'm checking that again and again.
Yeah. So a cyber physical system generally has got physical processes corresponding to the plant as well as physical consumption of energy resources by the processor, which is the digital part. And then there are cyber parts corresponding to the digital processor and digital processes, including the program, which is also a discrete system. Then you are having a third component, which is a communication, right? For instance, in this case, this line itself corresponds to communication, right? Of course, there is an integration between the physical and cyber happening inside the node, and also the communication, because all in all, the final functionality is being delivered by this entire system, right? Then we have to understand the essential characteristics of this embedded systems, cyber physical systems, or IoT. Basically, these systems most of the time are deployed in safety critical applications. For instance, imagine that there is an embedded system or cyber physical system or an IoT system that is deployed in an intensive care unit during corona care, let's say, right? What it does is, for instance, that embedded system or IoT keeps track of what is the consumption rate of oxygen by the patients inside the intensive care unit, and it reports to a inventory control that keeps track of how many cylinders are there in store inside the hospital, right? So what it does, if such a system fails, then the management cannot keep track of how many cylinders would be in need in future, and that creates a chaos, as we have seen during wave 2 of corona in the recent times in India, right? So these IoT cyber physical systems or embedded systems are taking form of various systems such as autonomous cars, robotic systems, drones, unmanned aerial vehicles, autonomous underwater vehicles, etc. and etc. Right? But no matter what are the incarnations of embedded systems, such systems possess the following characteristics. That is, they are the systems that require to deliver functionality on a real-time basis. That means the functionality of the system are required to be delivered on a timely fashion. Then such systems are non-terminating systems. Like for instance, if you take a lift control system inside your apartment, that lift system can never be turned off, right? That's why it's called as a non-terminating system. And usually such systems are infinite stated, right? As we'll see later what it means. Then as we have seen, it has got a plant that is behaving in a continuous fashion, and it has got a controller that is behaving in a discrete fashion. So it has got hybrid behavior. Then you have got heterogeneity, right? So heterogeneity means that there are various components that are having varying characteristics that are enabling the overall system. And as a simple rule of thumb these days, because of the increased demand on functionality, though more and more hardware capability is coming into picture, the complexity of the overall final solution is increasing more and more with every day into progression. right? Most of these systems do involve a human operator in the loop, and certain systems might be completely autonomous, where there is no need for human operator. Again, Dhruv, there is one more lady, Rashmi Sonar. Can you take her in?
Yes, sir, I did that.
But I'm still seeing like, okay, fine. So I can admit them, or only you should admit them?
Yes, sir. You can do that also, but I'm checking on that again and again.
Okay, fine. So basically, whenever we have such safety critical IoT systems, there are certain challenges because of the expected guaranteed behavior from such systems. What are safety critical systems in the first place? Safety critical systems are such systems which, when fail, might have catastrophic consequences, right? For instance, let's take the example of Bhopal gas tragedy in India, right? So had it been the case that when the gas was leaked, if an alarm has rang within a minutes of time, then people would have evacuated, right? So as a consequence of the failure of such alarm system, people were just sleeping in their homes and they succumbed to death because of the poisonous gas filling their lungs, right? So safety critical systems are such systems, if they fail to behave in a timely fashion, they have got catastrophic consequences, right? For instance, let's take an example for lift control system in a 100-story building, right? And usually, if a lift is serving a 100-floored apartment, usually the expectation is that it should be having an automatic braking system. That means if the thread gets broken, the brakes would deploy and the lift would come immediately to a standstill in the immediate next accessible floor, right? That is a requirement. But let's imagine that if the embedded system inside the such a lift fails to detect the detachment of the cable and the vehicle reaching free fall, then naturally there is a point of reaction time beyond which, no matter if you apply brake or not, the lift cannot be brought back to standstill condition, right? So these are the examples for safety critical system. Usually catastrophic consequences could lead to loss of life, as it has happened in Bhopal gas tragedy, or it could be having huge financial implications, right? So remember that huge financial implications often kills people also. It's one way or the other. So safety critical systems means if you are deploying such things in your business, or if you are using them as a customer, you should demand from the vendor that they need to prove their correctness with high confidence, right? What is the correctness? Correctness means that there should be an evidence that they behave correctly as expected. And all these days, when we say about the correctness, people always talk of testing, but testing cannot be of much use because Dijkstra Stace, a very celebrated scientist in computer science, says that testing can only show the presence of errors, but not their absence. But remember that correctness means absence of errors. That means testing alone is not sufficient to establish correctness of an embedded system or an IoT system. So these days people are looking for formal methods strategies so that they can prove the absence of bugs, right? So that brings us to the end of part 1. So Dhruv, can you enable microphone for the participants? I will take some questions.
Sir, I have to check with that.
Okay. Okay, you cannot enable the microphone for them?
Sir, actually, I'm the co-host. I'll request the host to do that. Just a second.
Okay, what you can do is, otherwise you can take the questions in the chat window, and if there are any questions, you can ask me. Because it's a 2-hour session, means people might lose orientation on what is happening in the class.
Yes, sir.
If
Yes.
you don't take questions right immediately.
Okay, sir. Sir, can we do that? The persons having any questions can raise hand, and then I would allow them to unmute.
What did you say, Dhruv?
Sir, I'm saying that if anyone has any doubt, I can. He could raise hand, and I will allow him to
Yeah,
unmute.
fine.
So yes,
Fine.
sir.
So anybody of the participants, if they have got any question, please
They can
raise your
raise
hand.
hand, so
The
I
host would
can
give
give
the
them
microphone
permission.
control to you. Okay. Okay, fine. Then we'll continue to the next part of the course. Right. Are you seeing my screen, Dhruv?
Yes, sir.
Right. So on the other hand of the spectrum are these concepts of autonomous IoT systems or cyber physical systems. What they mean is such systems means these are the systems with the capability of self-governance, right? For instance, self-driving car, right? If you see Rolls-Royce or Benz or Google car, they are trying to develop a system or a car that can drive on its own without the need of a manual driver, right? So what such autonomous systems mean is that they can set their own control objectives and accomplish their mission goals, satisfying these control objectives, planning the course of actions to achieve the goals, right? First thing is, setting the control objectives and then defining the goals and then planning the course of actions to achieve the goals. That's sufficient to be called as an autonomous system. What are the challenges such systems face generally is that designers have designed such a system hoping that the operational environment would be satisfying certain criteria. But when the system is deployed, there could be certain deviations bringing which trigger certain uncertainties in the system. And they should perform in the expected manner for extended periods of time, right? Because learning might make them notorious, right? And then there could be, it could involve controllers implementing high-level decision-making techniques for reasoning under uncertainty and to act accordingly. Requires intelligent autonomous controllers, right? There are various examples like drones, medical robotics, AI-enabled robots or service robots at the home, autonomous underwater vehicles. But let's understand what is the concept of formal verification. Formal verification is a technique of application of mathematics to solve the system correctness problem. What is system correctness problem? Any system is devised or designed keeping in view certain requirements, and then we solve those requirements and implement the system. So basically, at the beginning we have requirement, at the end we have the final system design. So system correctness problem says that we need to establish mathematically that D indeed conforms with the requirement R. Right? So that is how the things are. And generally, this formal verification involves formal specification and then proof methods like this. For instance, if there is a real-time IoT and if there is a required property on that system, what they do is we formalize that system as a formal model M, and then we formalize the required property with formula phi, and using a proof methods we establish that the model M or system M possesses property phi, right? If it says yes, then we have evidence. If not, we have evidence for why it fails. So such formal verification could be applied at various phases of the system design, right from the conceptualization phase, requirement definition, design phase, implementation, and all that stuff, right? So basically, when a concept is being formalized, we can do a concept analysis, requirement analysis, design verification, implementation verification. There are several formal languages and tools exist, each applicable in every phase, right? So let's not look to it. Just pay attention to this slide. It's very interesting and more illustrative. Let's say some system is there which has been initialized. It's an IoT system, for instance. And let's say there are 3 program variables in the system, X, Y, and Z, which are initialized to value 1, value 2, and value 3 respectively. So that green ball shows the initial state of the system. And then it visits the next state. where XYZ values change. Likewise, it's changed. Then accordingly, it transits to the new state. And at certain point from this red ball onwards, there is a possibility that system might have two different trajectories. It might go left or right, and accordingly, we will continue, right? So we go forward, and then the system might evolve in multiple trajectories, right? This is how the state space of the system becomes infinite. Usually in cyber physical systems, the number of types of states visited is often infinite, right? However, if this is the set of states visited or sequence of states visited by your system, and if you are talking of correctness analysis, then what you should do is you should compute each of these paths. Maybe there could be finite number of paths or infinite number of paths, we don't know. And then we should check that whether each of that path has got correctness criteria, right? Computing all the distinct paths of system frontiers is not always possible, partially due to that the paths are non-terminating and often has infinite states, or otherwise it could be that the computing algorithms might suffer from non-termination. On the other hand, people have shown in the research literature that there is no need to compute this. For instance, these are the three paths I am showing, that they are nothing but taken from here. This is one path, this is the other path, and this is the third path, right? So basically I have enumerated them. It is sufficient that it's not necessary to compute the path itself, but it is sufficient that we can compute the set of states visited by such system, right? So if you compute such a set of states, even then we are able to solve the system correctness problem. So basically it might look easy, but there are various challenges because systems are continuous and infinite stated. That means if you are trying to solve such a infinite stated systems verification, then often you might run into non-decidability, right? Then you have got non-terminating infinite runs, which I have already illustrated. Then there could be other challenges such as requirements could be temporal, right? For instance, let's go back in here. Let's say the requirements could be temporal, means that blue ball that is visited in here, the requirement could be that this blue ball signifies proposition P and this green ball satisfies proposition Q. Then it says that the state of the system would be satisfying proposition P within 5 steps after the system satisfies proposition Q, right? So it's a kind of temporal requirement, right? So safety critical systems are everywhere, and for that reason software reliability becomes very important. In the past, there have been a lot of important missions that have failed because of software errors. These are examples, like for instance, what you are seeing in here is a Ariane 5 maiden launch, which has failed due to a software bug within 40 seconds after ignition. And what you are seeing in here is a cancer treatment machine that subjects to the patient in here with high intensity radiation, right? So that is what. So what happened was, in this case, this is a machine in Canada, Canadian manufacturer. So the patients who are treated in here, at least 5 to 6 people have died because of wrong operation of the electron gun, right? So we have developed a tool framework. I will not spend time on this. Let's go further. So we have developed a synergistic tool framework by doing a theoretical analysis as well. So we can take any system whose LHA model, and we can establish whether the model is correct or not. Of course, we have got certain constraints to be satisfied by the initial LHA model, right? So with that, we finish part 2 of formal analysis frameworks that we could use for IoT approach. Then with that background, that lets us to start the domain or pure discussion in Internet of Things. Let me zoom in. Is my screen visible, Dhruv?
Yes, sir.
Okay. So this is the Internet of Things. Mostly this is the work that we have done in early 2015 and 16. We have developed a one IoT protocol, which is now being practiced by various people, but we did it for the first time in 2015. So Internet of Things are embedded systems that are enabling various things in here. For instance, what you are seeing in here is this is a utility system in here that is keeping track on how much bill is being generated by various utilities that are being used in the home, right? For instance, there could be a kind of sensor that is keeping track of your cameras in the home, right? There could be some Internet of Things that are used in manufacturing domain, right? And there could be an entire value chain that could be derived by interconnecting those things, right? So we'll just take a look at it. Let's understand, first of all, what is an Internet of Things, right? Everybody, when we ask students in various IITs or everywhere, they'll say that I can connect by coffee machine to internet. So it will be concerned, but that's not a very scientific definition. So, generally speaking, what we have is this in Internet of Things, we have devices that possess either one or all of the sense, actuate, report, computing kind of behavior connected via internet, right? That is what is called as a Internet of Things, right? Why it matters? It really matters because a lot of Internet of Things based deployments are happening. At least, it is said some hundreds of billions of such devices would be operational by the year 2025. IoT enabled devices are becoming ubiquitous, right, across various domains. There's a need for guidelines, frameworks, and an associated protocol for such devices, so that, when you have got billions of devices and we only have handful of companies, that means there is room for several other manufacturers to join as vendors and start making profits out of the business value they can create. So there could be an opportunity for various original equipment manufacturers to make their existing devices IoT compliant, thus making the devices forward compatible. And then it would help the newcomer companies to get started with IoT device development. Tomorrow, some of you might start a company, right? So if you understand IoT protocol, then you can work on making your device as a IoT compliant device. So let's take a look on, some kind of background on internet. So internet has started, at least in India, in late 90s, like 92, 93. But now you can see, by virtue of Jio, ATAL, and all that, so internet is a kind of domestic word these days in India, right? No matter whether it's a rickshaw puller or an auto driver or a cab driver or a pilot or a defense personnel or a minister, everybody is hooked onto internet via their smartphones, right? So you can see the impact of it. And same is going to be the impact of Internet of Things on our day-to-day lives in the coming few years. So internet has improved technologies and solutions that existed before internet has come, right? For instance, we have got our railway reservation system. That was far before internet came. But before internet was implemented, we used to have a manual reservation system, right? Like every railway station in India would be allocated some 10-20 as their local quota, which they can sell if a passenger goes there and applies for a ticket there, right? That process already existed, but its value got appreciated and its quality of service got appreciated because of the advent of internet, right? Because nowadays we can go to any station and we can do a reservation, or we need not go to a station, we can sit at home and buy a journey ticket from station A to station B by sitting at station C. Of course, because of the sparsity of the IP addresses, people are talking about IPv6 that brings in billions of IP addresses possible. There are various household appliances. For example, air conditioners, we might have seen Panasonic has got an internet-enabled connectable air conditioning appliance. Then there are light solutions from Crompton Philips, which gives the owners a possibility to turn off their lights and on off their lights through their mobile phones through certain apps, including the switches for heaters and air conditioners, right? People, for instance, I think Mercedes and Volvo have already got an IoT enabled, car start system. For instance, if you are in Dubai, right, for instance, where the temperature is sub 50 all the time, and if you want to drive out and you are moving out from your air conditioner in your home, but there is 100 meters to walk where the temperature is 50 degrees, right? But you need to again turn on the AC after you sit in the car. Alternatively, if an IP based ignition system is there, through successful secure login, the owners can directly turn on their AC, of course, after igniting the system, igniting the engine, to the comfort of their mobile phone, by setting a time or predefined time at which point the AC should be turned on. We have got IoT enabled other things such as vending machines, laundry machines, information signposts. For instance, information signposts. For instance, you might have seen in big cities like Gurgaon, or for instance, Bangalore, Hyderabad, Pune, there are huge electronic display panels, right? You can imagine in the future where the vendors who are owning those digital display panels can put a tag on it, right? Saying that I can display your ad if you give me 2000 rupees per minute, right? And then and there itself, you can just negotiate with the vendor, and by doing an online transaction for 2000 rupees, your advertisement could be there instantaneously before your eyes, right? Like that. You have got industry specific devices such as smart cupboards in a library, inventory goods in a godown, vehicles with onboard electronics and diagnostic systems, scientific gadgets such as GoPro, Tide Gas. These days Ray-Ban is working with Facebook to make certain smart glasses. Wearable devices such as fitness bands. You can see Fitbit or Google Watch is also having these fitness devices. It's a simple thing. It keeps track of oxygen levels in the blood by means of certain advanced imaging and also pulse tracking. By reading just oxygen concentration in blood and pulse, everything by virtue of AI and ML, you can prognose various body phenomena. Imagine the value the same device offers on getting them connected to internet. Right? That is a value proposition of moving these systems onto IoT. So as of 2014, we do have, as of now in the IPv4 domain, 2 billion connected devices as of 2014. Right? At least 8 billion devices to be connected. I mean, this is what has been. I think these numbers are even elevated now. IoT market value will be greater than $1 trillion. Of course, these are taken from a standard research report. These are not cooked up numbers. 8 billion devices could not be produced by a single company alone. This is where the opportunity exists for various companies to chip in and then contribute to various systems. Right? Heterogeneity increases with disparate domains and requirements as well. IoT's heterogeneity is visible with a large number of its definitions. For instance, in 2015, 2012, I think, IEEE has published a book of definitions for IoT, right? That means there are several definitions for understanding an IoT by various people, right? So what is the degree of heterogeneity in IoT devices? For instance, some devices would use simple Wi-Fi connectivity. Some people will use Bluetooth, low energy version of Bluetooth. Then near field communication, then RFID based communication, or a simple traditional SMS based communication, or a GSM based voice communication. And the domains of deployment are very diverse: medicine, governmental, industries, household, traffic, transportation, communication, you name, you will find one deployment of IoT there. And there is a platform related diversity, various operating systems, various hardwares, and then there are many proprietary solutions as well, right? And what it means is, because of this reason alone, there are various security and control related challenges, because as soon as the device becomes online, by virtue of the opportunity it provides us to be discovered by everyone, it also exposes its vulnerability to be, cyber compromised. To overcome all these things, we have proposed one protocol and an associated framework for the protocol. So that protocol that we have developed satisfies these requirements. It is independent of the communicating media platform, on-demand discovery and learning about the new things on the fly. It will provide access control. It will be able to control accessible devices easily, and it is forward compliant with respect to the framework. And what is the framework that we have proposed? Such a framework will abstract away any low-level details. It provides minimum infrastructure for any IoT-enabled device. Every single time a new device needs to be made IoT ready, right? There is an opportunity for new vendors to chip in. And then such a framework should be unconditionally forward compatible. It should not be that, if a new device comes, then I need to upgrade my protocol. No, not there is no need for such scenario. Right. So we have proposed our work, and then we published it in CITES 2015, as well as we have got a follow-up submission in Reliable Intelligent Environments in a journal, and then we also have another journal in Inter Science. So essentially, in our protocol, we take this reference architecture as our deployment form. So we have got a cloud where we are having various vendor registration portals running. Then there's a network connectivity via the ISP service provider. Then you have got IoT nodes that are going online through this ISP service provider. And then there's a user agent, right? User agent could be a simple web interface on a mobile phone or a computer, or it could be a kind of Bluetooth or Wi-Fi enabled phone without the need of getting online or getting access to internet. For instance, in our architecture, we have following classes of nodes. We have client nodes, right, through which IoT devices are accessed, which are these user agents, right? Then we have got thing nodes, which are these IoT nodes, such as bulb, whatever are being the objects of control. Then we have got cloud nodes, whatever are the web interfaces that are residing on the cloud. Right. So based on this work, we have given first time a very clear definition for Internet of Things. I request you all to go through it rather than just giving some random answers, bringing your coffee machine to Internet means IoT, right? So let me read it out. Internet of Things is a worldwide network of interconnected devices that are IP enabled, hence interconnectable and uniquely addressable based on standard communication internet protocol. It also includes internet services, monitoring and controlling those devices, right? What is the definition for an IoT node? IoT node is an embedded device comprising of a microcontroller or a microprocessor with IP network interface and sensors and or actuators, right? That is how we define as an IoT node. What is an IoT device? If a device qualifies to be an IoT node as we defined earlier, we call it as an IoT enabled device or IoT device, right? So this is our, for instance, if I want to take a look on what is the architecture of our IoT node, this is how it looks like. So this microcontroller could be microprocessor depending on whatever is available. So this microcontroller has got interface with the sensors. It has got interface with the actuators that lets us to control an entity through the sensor and actuator. Microcontroller senses whatever is happening inside the entity and it computes the actuations and drives out through the actuators. However, because such embedded systems are networked through internet protocol or IP protocol, so there is a need for a communication module, and that is being satisfied by this communication module in here. Depending on how many communication mediums are there, accordingly we will be having those interfaces. For instance, it would be having an Wi-Fi interface, it would be having an Ethernet interface, it would be having a USB based communication or Bluetooth and NFC, right? So how much time do we have, Dhruv?
Sir, you have 30 more.
30 more minutes, right? Okay, okay, fine. So we'll continue in here. So typically, the IoT architecture consists of remote hosts on which the things needs to be registered. Then there is a connectivity layer through which devices or the IoT nodes or IoT things talk to the remote host or among themselves, right? And the nodes themselves. Consequently, any IoT device original equipment manufacturer shall provide remote host service for thing user ownership registration, which is quite normal. Then you need to have IoT nodes with certain minimum behavior, right? And the IoT architecture that needs to be implemented to make any device to be IoT compliant is like this. The IoT node should have the following minimum behavior. It should receive commands from authorized remote hosts and user agents, execute the commands accordingly, periodically reporting operational status and sensor information to authorized remote hosts and user agents, and configuration, right? These are the things that are expected. So take a look on our reference CITES 2015 paper, which explains the things in more detail. So with that, we come to end of part 3. So we are doing good. Then we start our part 4. Right. So this is about the real-time kernel that we have developed as part of our of my earlier work in Denmark. Right. It is done like some 15-16 years ago. So what is a real-time kernel? Let me explain you something. Generally speaking, let me. Is my screen visible, Dhruv?
Yes, sir.
Right. So generally what we have seen till now is, there is, let me draw this. There is hardware, right? Of course, it is also having your sensors and it is also having your actuators. And we added to it communication module through which IP enabled communication is possible. And we are calling this as all in all is a IoT node, right? This is how we have seen. But let's understand that from a different perspective now. Because when you have the sensor, actuator, hardware and all that stuff, what is important is there is an algorithm that is implemented in software, right? So generally, if you want to implement some software for an IoT, then you need to take care of two issues. One is hardware specific matters and timing related things, and the other thing is application specific requirements. So if you go for operating system based implementation of IoT, application programmers can be more efficient and the application development becomes a kind of breeze activity, right? So we are considering to see, let me remove this. So instead of using OS, we can use a lighter version of OS called as a kernel. And application software can be written on top of the kernel. Or basically, these two could be jointly compiled, right? So that is an advantage of using kernel in Internet of Things deployments. So let's go through the slides for this. Okay, let me right. Right. So in this work which I have done some years back, I have developed a real-time kernel that could be used for IoT applications. We have demonstrated its latest version. It is Harshark Micro. We have done that. So what is it showing is real-time kernel with following requirements. It should have a small memory footprint, small memory overhead. You should remember there is a huge amount of difference between footprint or code footprint versus memory overhead, right? Code footprint means the size of the binary that is generated after you compile the source code, which is used to flash the microcontroller. On the other hand, memory overhead means how many data structures that we are using, like size of arrays, size of dynamic memory, and all that stuff. So generally, and on the other hand, the kernel should be very fast, very powerful in terms of responsiveness and predictability, right? So it should have minimum jitter and all that stuff. Kernels still employ the conventional data structures, which result in big processing overhead. But for instance, what is the disadvantage if you go for larger data structures? Then what happens is basically they lose in terms of performance, right? And of course, the cost of the hardware might increase because more costlier hardware is required to accommodate such kernel data structure heavy operating systems. Right, let's not look into that. Generally speaking, if you have most of your faculty, so any operating system need to provide process management support, event management support, timing management support, resource management support, task synchronization, communication. Right? In the same way, the real-time kernel should also provide support for these functionalities. Right. So I'll not go through this because we only have 15 minutes left as of now, I can see. So I'll just quickly introduce you through the architecture of the kernel that we have developed. So this is how the block diagram of the architecture of our kernel looks like. So you can see everything is implemented as a standalone module, and they are integrated during compilation using an appropriate compilation script. So at the bottom, which is talking to the hardware, is your hardware adaptation layer. And hardware adaptation layer provides primitives that could be used by your task manager, which is scheduling various user tasks or system tasks or the hybrid. Then this task manager also talks with the resource manager, which in turn is managing the resources. And then you would be having a kind of, the interaction between these tasks and event manager and resource manager is being accomplished with this software bus. This hardware adaptation layer is the guy who is interfacing with both hardware and the external world, which is receiving external key interrupts and timer interrupts and other specific interrupts. So basically, whatever you are seeing in here, this is your application software task. Maybe some of the tasks could be very specific to the communication controller. So the kernel that we have implemented makes use of binary vectors. There are no queue data structures in our system. It accomplishes integrated event and timing management. It even accomplishes integrated resource and task management, instantaneous notification by a Boolean vector semaphores, communication technique of content-oriented messaging. There is a clear-cut scalability that is made possible because of our smart secondary level scheduling possibilities, and then compatibility with various hardware, because compatibility comes an issue if this hardware adaptation layer is mixed with everyone. Because of the separation of our hardware adaptation layer, if you want to come, make our kernel compliant, we just recode this hardware adaptation layer for that specific hardware. Right, and then it is a layered or modular architecture. Depending on the need, we can turn on or off of some or one or more of the components or modules. It has a secondary level schedule, right? So let me illustrate with you how we have overcome the concept of queues in our real-time. For instance, let's consider, we want to have a queue of length 16 units, right? That means in the queue there could be 16 process requests, right? For instance, if there are requests loaded, so what we can do is, if this is your queue, right, and I'm using the 0 to 1 because we use binary encoding. It could be starting from 0, any entry could be there between 0 and 15 if it had been a queue. But let's see how we can overcome this by using a binary vector of this form. So remember that, okay, let me do one thing. Let's say, let me use my hand. For instance, this is your queue, right? Let's consider. Let's consider there are 16 element queue, right? And the entries could be 0, 14, 15, 3, 3, 4, 5, like that, right? That means this is a queue holding requests for various real-time tasks from the application. Now let's remove the queue and let's have a binary vector like this, right? This is our binary vector, and if you can see, you can identify each of the bits uniquely by their bit position, right? 0 is a units position and 2 it's like this. So now previously also we had 16 tasks. Here also we have 16 tasks whose IDs could be task 0, task 1, task 2 to task 15. And let's say if I want to have a request for task 15, I put a number 1 here. If it is like task number 7, I don't have a request, it would be 0. So basically, by replacing this, we can completely replace the concept of queue, right? And we can use the concept of binary vector, and we can still maintain the behavior that is promised by your queue, because the presence of 1 means there's a request for this task ID. In the absence of 1, that means if it is 0, that means this task is not currently in the ready queue, right? That is what it means, right? I hope that is clear. Let's continue with the slides. Right, so we can have such a interpretation of ready queue with Boolean vectors, right? So basically the position of the vector, where position of a bit in the vector could be identified for the process, and then whether that particular bit is set or not means that particular task is there in the ready queue or not. Each bit is mapped with one user task. The bit's position in vector is used as an ID to the user task. The bit's position in vector is also the priority of the user task, right? And now what we can do is the bit position could be used to map the contents in the table, right? So basically by using function pointers, what we can do is task 4, if it is set, is the highest priority task that requires you to schedule task number 14. Right? Typically, task management looks like this. This is how an operating system looks like, but in the kernel, it is like this. Tasks might talk directly to the hardware and kernel manages the tasks. Let's not look to this. It is a bit involved. This is how, from a very high level, maybe not many of you have seen how a Linux kernel is implemented, but in essence, this is how kernels in an operating system are implemented. So there would be a, if you are implementing in C or C++, there would always be a main function, which essentially does two steps. One is initializing the hardware, and second is starting the kernel, right? Which in turn, when you initialize the hardware, what it does is, it depending on the hardware that you have, if it's a microcontroller, you will be initializing the ports and application interrupts very specific to the application on which is going to be deployed with this kernel. And the start kernel, essentially what it does is it checks if there is any active task in the active task vector, then it invokes the call schedule. Essentially what a schedule does is, basically it keeps an eye on this entire ATV vector, and if ATV is not equal to 0, that means there is one bit set and it identifies the most significant bit, and that particular task is deployed or scheduled, right? That is how things are done. Right, so now generally we have used, whenever we talk of operating systems and schedulers, we talk about the problem so-called as, deadlock, unbounded priority, and all that stuff. To overcome that problem, we have used and very sophisticated time tester protocol called a stack-based priority ceiling protocol, which consists of rule number 0 and 1 and 2. Essentially what it does is, a stack-based priority ceiling protocol ensures that a task can only start running if all the resources it might require during its lifetime are available. That is the simplest rule it implements. Let's not look into this. Basically, in the kernel are two calls corresponding to the resource blocking and resource unblocking and all that stuff. So we have got task preempt, illustration of preempt, right? Preempt usually what it does is, when a preempt is invoked, it if this is the running task, the context of the task is saved, like it will be going into the stack like this. So on invoking a preempt, it invokes a save. That means the task one context is saved in here, right? Then once task 2 is released, because task 2's priority is greater than task 1, it gets scheduled and it starts executing. And if, say, at some point task 4 comes, then the scheduler preempts this task 2. Then what it does is it saves the priority, it saves the task 2's context on the stack, and then it continues. Corresponding task 4 starts running. Because something is wrong with me. It's not working. Let me close some of them. Right, generally, as I illustrated here, let's come back in here, right? So right, so this is how the task scheduling happens. We have implemented a two-step communication protocol, rather than, if some task wants to communicate with other task, what we do is we do not waste synchronized communication, but instead we do a kind of non-blocking style of communication, where whenever there is a communication of certain variable name, what we do is we first broadcast, and whoever are the tasks that are interested in that variable name, they would be notified of the availability of that contents of that variable name and its address. And whenever those tasks become running, only then they start executing the receive on the variable name they are registered in, and then only they will be starting to copy the content. Doing so, what happens is Had it been the case that such a protocol is not in place, then it would be a synchronized implementation where whenever there is a communication call, irrespective of the receiving task is in the focus or not, time is spent in copying the contents from the source buffer to n number of destination buffers if n number of tasks are interested in that process. Right, so this is what is happening. We use broadcast message signal, and whenever a receive happens, it invokes internally copy message. So essence, this is how the architecture looks like. We have a hardware adaptation layer, which is handling the beep interrupts as well as tick interrupts from time to time, which are being processed by the IEM, which talks with task manager, user task, software bus, and all that, and it gives the required behavior. And this is our secondary scheduler. That means if there are more tasks than the 16, then what we do is we implement a secondary scheduler as an algorithm into which we register the other tasks. Right, and again, the secondary level scheduler could itself be implementing FIFO, static, cyclic, and all that stuff. So in essence, what we have done is we were able to implement a real-time kernel that could be used for IoT applications, where one of the higher priority tasks could be taking care of the communication controller. Thus, we can accomplish the internet protocol based communication by making this high level priority task as a communication specific task. Right, so I mean, this is not important. So yeah, so that's how we have gone through. So let me come back to the original set of slides, because we said at the beginning that we'll be covering to these three parts. So we have quickly gone through at the beginning. This is a summarization of the slides. So we did this part. Then we have seen various incarnations of embedded systems, right? And then we have looked into server physical systems definitions, and then Internet of Things definition and WSN definition. Then we have also covered what is the thing we have accomplished in our group. And then we have just now finished the set of, the software stack of real-time kernel that could be customized for IoT deployments. Right? That's how the things are possible. Right, so maybe that was a little bit quick because the time was slow, that the time was less, and the contents were high.